So thank you all for coming, and it's a bit of a tech talk today, but hopefully you will still find it fun and get something out of it. We're going to talk about GPU as a general processing unit, and I'm so happy that I didn't scare 90% of you off with that title. So as a bit of an introduction first, why am I here on stage? I made this asset for the asset store called TC Particles. Maybe you've heard of that. Or you were at the talk just before this one of Museum of the Microstar. The particle system in there, I built that. And you might have noticed about those things that they're a little different than usual particle systems, where instead of having 10 or 50,000 particles, which is a lot, but you can have millions of them. And that's not voodoo magic. That's done by using hardware acceleration, using the GPU. And today I'd like to talk about how to use that in your own games, because it's an exciting technique. So why does that work in the first place? Well, I'm sure as many of you know, a CPU is just this clunk of maybe a few big cores. We're up to quad cores or even hexa cores right now. And they have massive pipelines, and there's all kinds of smart people working on making them as fast as possible. Whereas the GPU, though, is a lot of really small cores. They're very specific cores. They're only good at some instructions. But when you can make something run on that and run it in massive parallel, you can imagine just how much more raw computing power you're gaining out of that. And then there's some other stuff where a GPU just has much more memory and is much more, much more raw amount of flops, floating point operation per second, and we can benefit from that. From now on, I will just call it GPGPU instead of general purpose computing on the graphics processing units. I have 30 minutes, I'm not going to waste that. All right, so before you jump in and make your entire game as a compute shader, which is a fun challenge, but it's not really practical. It's only beneficial if you can do, if you can manage a few things. First, your problem obviously has to be able to run in parallel. If you have something that is inherently sequential, you cannot run it in parallel and you cannot benefit from running it on your GPU. So the second thing is that this one's a little less obvious. You have to be, the system has to be really modular from your game. Like a particle engine, it's great that you have these effects in your game, but they don't interface with the rest of your game. Maybe they collide with the world, so and those kind of things, but it's not like when a particle hits the player dies or something. And that's because the GPU is such a separate system from the CPU that you are stuck with this bottleneck on communicating between the two of them. You can communicate from the CPU to the GPU. I mean, you kind of have to. And I think you have a bandwidth of about, I'd say, at least a gigabyte per second there. But communicating from the GPU to the CPU, at least in Unity, isn't feasible. Doing so can lead up to spikes of 100 milliseconds in your game. So you might be able to get away with that for, say, generating a height map or for a terrain or something. But at least in real time, there's no way you can pull it off. Thirdly, it's a cool technique, but if you want to have some fun with it, go ahead. But again, you do actually want to carefully consider if you actually need it and if you need more performance or just a bigger scale in general. So examples are, well, the particle engine, obviously. I'll be using that as an example throughout my talk since that's what I do. Mass physics. Physics has been floating around for years, and it's using these same techniques. Mass AI, you can imagine simulating a flocking of birds on a compute shader. Or, interestingly enough, there's also some graphics techniques floating around using this. Global illumination sometimes uses this. There's some stuff floating around with very fast ambient occlusion stuff. The picture of this is actually of the forward plus rendering technique, I believe. That's running on a compute shader as well to do this render hundreds of lights, not in dereferred rendering. It's cool. Okay, I find it cool. All right, so if you decided, cool, I'm going to build a GPGPU application, let's do it. So how do you do that? Well, you have a few choices right now. There are 3 dominant languages. The first one is CUDA, and I think it was not only the first one on the slide, it's actually the first one to be created, I believe. But it's a nice, kind of compact-ish C language, but it only runs on NVIDIA cards, so really Unity will never support that. It's not that it's just not portable. It's cool for supercomputing, but other than that, eh. So the competitor came, OpenCL. OpenCL is really nice, where it runs on NVIDIA, it runs on AMD, and it can even run on your CPU as a fallback for your GPU. The syntax is messy, but in a way wonderful. And I do hope that Unity will support it someday. They have been talking about it a little bit, but I wouldn't get my hopes up too high. So then we are stuck with the third option, direct compute, part of the DirectX11 framework. It's what I used. It's written in HLSL, which is the same as what Unity uses for their shaders. It's a neat language because it's part of the DirectX11 framework, which you're using for the rendering of your game anyway. You can share the same resources, you can share the same knowledge you have of writing shaders. And in that sense, for games, it's actually one of the best languages to do this. And then there are a bunch more of other options, but those really haven't established any user base yet. All right, so DirectX11 has this system called Direct Compute. And in Direct Compute, you write these things called compute shaders. And they look like regular shaders, but there's some differences between them, so I'll give a quick overview. So the goal of these compute shaders is to enable you to run not only rendering stuff, but general algorithms on your GPU. So as I said, it's written in HLSL, and it's separate from the entire rendering pipeline. You can see there, DirectX11 has a massive rendering pipeline at this point. Compute shader is a separate island from that. It shares the same data, but it's not run at any particular point there. So as I said, you share the same resources. And the cool thing is where you used to, with the rendering pipeline, you can draw geometry and those kind of things. And indirectly with that, you are invoking threads on your GPU. But with a compute shader, you can just explicitly say, give me 100 threads to run this code. All right. So on running these threads, they made the decision to have you split the threads into thread groups. You cannot just run a singular thread. As you can see here, there's a group of 16 by 16. You can actually also make 3-dimensional thread groups, but let's keep it flat for now. And you can then dispatch a number of these thread groups. In these thread groups, you get some stuff like shared memory. So you can share memory globally for that thread group, not globally in your GPU, but globally for that thread group. And in practice, you use the num_threads attribute for your kernel. Don't worry, we'll go over some code where you can actually see this in action instead of having this abstract thing on the slide. So yeah. All right, so obviously you will need some input and output for your computations. And for that, they have chosen to make this new resource type for DirectX11 called compute buffers. There are 3 types of them. One more useful than the other. The first one is where you can have a raw byte buffer, and you can directly address, I want that byte of the buffer, which can be cool, and you can actually only store uints in it. It's really fast, so if you're really bound on performance, you can do some trickery with that. I wouldn't advise it because it makes your code just a mess. Then there's the normal buffer, so that's the first one in the blue area you can maybe see there, where you can just store floats. This is for a lot of image effects, maybe even for a very simple particle engine can be cool, and again, it's quite fast. And then there's the structured buffer, which is the really cool thing, where you can define the struct, so just a small packet of data, and then have a buffer, basically just an array of those. Each buffer has some attributes. The most important being that you can make it rewritable. Keep in mind that since on GPU, memory is a bit different. By default, you cannot write to it. But by appending RW to the buffer, you can get a rewritable buffer where you can store your output. Lastly, a buffer is just a big array, a 1-dimensional array. If you need 2-dimensional arrays or even 3-dimensional arrays, you can use textures for that. They improve textures for DirectX11 to do some more cool stuff. So as you can see there, we have a rewritable texture that takes floats in the blue area. All right. So I think it's enough with the abstract talk. I think we should go to an actual example. Oops. There we go. OK. So we have a bunch of these particle controllers here, and each of them runs, let's see, 100,000 particles. So we have 9 of them. And then if I hit play, it should. All right. So we get this big glowing sphere, and each of these little dots, maybe I can zoom in on them and you can just see how many of them is a particle individually simulated on the GPU. Then there are some forces working on them which are pushing them outwards, and based on their speed they get a different color. And they also each have a different texture, and hopefully you agree with me that it looks neat. So how is that done? Well, let's go over the code a bit. All right. So 3 parts to this. We first have the compute shader, which, as I talked about, is what does all the calculations in parallel on the GPU. There's the C# script, which controls it from the CPU side. And then finally, we have one, well, normal, quote-unquote, shader, which draws the particles. So let's go over the compute shader first, just real quick. I don't have that much time, so I cannot go too much into detail about this. But first, we tell Unity that we define this function called a kernel. And that is the code that gets run on the GPU. So we can see that we have defined it here. If you don't specify this, you cannot interface with Unity. So then we have the particle struct, so just the data packet for each particle. We have a position, velocity, and a color. Then we make a big, ginormous buffer of all these particles. We're going to go over that later. So then let's see, in our kernel. Well, first we have this attribute here, which I was talking about, num threads. This means that whenever I call dispatch from my CPU code, that we get 128 threads running in one group. For a particle, it obviously makes sense to have one thread for each particle. So in this case, one group just means that we're going to simulate 128 particles. So how we actually simulate the particles, we figure out some cool way to set the color. So you can see that we set the color by reading from the texture. I will come to this a bit later because how to read from a texture is a bit different in a compute shader than it is in a normal shader. This is some kind of force that pushes them out of the center in some interesting way, and really the math doesn't matter that much. You can see that the particle buffer, we just addressed it as a normal array, so you don't have to worry too much about that. And then finally, we apply the velocity. So about those textures real quick, I want to address that because on the forums there was a lot of people screaming, how do you do this? So firstly, you have this texture object, which holds the actual texture data. But then the confusing thing is that you also need this object right here, a sampler state. What this holds is some info like I want the texture to be bilinear sampled, and I want it to be those kind of things. The naming of that, I don't know why Unity chose for this, but it's very, you have to be extremely precise. You just need your name of your texture and append sampler to that. Only then you're getting the Unity settings for the sampling type, for the MIP mapping type, etc. Then finally, to actually get the data out of that, you call this function called sample level on the texture object and pass the sampler in there. And you have some UV coordinates, you specify the MIP level, and there you go, you have a color. All right, so for the CPU code isn't all that interesting, so I'm going to skip over it quite quickly. So we have a bunch of variables. We get the compute shader just assigned in the inspector. A compute shader is just an asset in Unity. We define the same struct here as in our compute shader, so we can upload some data. We have the compute buffers here. I will come to this in a bit. And then for the setup, we find our kernel. So this is the interfacing you do with Unity. You have to find your specific kernel. When you create a buffer, you have to specify two things. Firstly, the size of the buffer, which is just like you would specify the size of an array. We want num particles in our buffer. We have, say, 100,000 particles, so we need our buffer to be 100,000 long. The second argument is the stride of the buffer. And what's that to say is the amount of bytes for each element in that buffer. In our case of our particle, we have 9 floats, so that's 9 times 4, that's 36 bytes. So I can advise you to just store that in a variable somewhere. You can get it auto-generated, but that doesn't work in a web player, so just stick with this for now. All right. So we generate some random particles, and we upload those to the buffer. Again, I'm just skipping over this quite quickly. I'll come to the rendering a bit later. So for the updating, you have to do 2 things. First, you need to send those resources to your GPU so it knows how to use them. And secondly, you dispatch the threads. So in code, we bind the resources, we set the buffers, we set the floats, we set the texture. And secondly, we call dispatch. Notice again that you're not dispatching a number of threads, you're dispatching a number of groups. All right. For the rendering, I could have chosen to do this with a geometry shader, but in my test, geometry shaders are horribly slow. I don't know why. But so what I did here instead is use a compute buffer again. We have this compute buffer of our points of a quad. And to set that up, we just initialize some vectors. And you can imagine that this represents 2 triangles in the form of a quad. To actually render them, all these quads, what we do is we have this material, again, just assigned by the inspector. We set the buffer on them of the particles. We set the buffer on of the quad points. And finally, we tell Unity to draw with this material, and then we do this draw procedural call. What this does is that it launches the shader that your material uses, but in a particular way. This is quite a normal shader, except for the vertex shader, where instead of having a mesh as an input, so a vertex as an input, what we have as an input is just these 2 system variables. Firstly, we have the ID of the vertex. So for our quad, this ranges from 0 to 6. We first have our 0th, then our first, then our second, then our third, our fourth vertex. And then we have the instance. So for each instance goes from 0 to the number of particles we have. So since we don't have any data, we need to pull our data out of those compute buffers. So you can imagine that we just get the nth instance out of the particle buffer, get its position, and then we can do some math magic to, with the quad point, generate the appropriate position to be able to draw a quad. And from there, it's a shader just like any other. I have a fragment shader here, and I could do whatever in here. I could multiply the color by 2 or whatever. So other than that, it's really not different from writing shader code. So and then just finally the setup in Unity, where each particle controller, as I said, has these assets assigned in their inspector. This is just what a compute shader looks like in the Unity Project Explorer, and it's an asset like any other. All right. So I'm just going to run the demo again, overly bright because I did the ×2, but yeah. All right, so that's what you end up, and that's not bad for just, well, I'd say about 150 lines of code. All right, back to theory. So writing compute shaders is actually pretty straightforward, and I did a good job of not making it overly complex to get the most out of it. But there are some things that you do have to keep in mind if you want to get the most out of it. Firstly is that for the thread group size, what you'll want is a multiple of 64. The reason for that is of how a GPU architecture is built, where these threads aren't run one by one as they would be on the CPU. They're run in these waves. And for AMD, this wavefront size is 64. For NVIDIA, it's 32. But what that means in practice, if you would have a thread group size of, say, 50, they would still be launching 64 threads, and you would just have 14 threads doing nothing. There's no way for them to split that in smaller units. So stick with a multiple of 64. Secondly, group shared memory. So that is memory that is global to the group. If you can get away and use that for caching for something or storing the results of some calculation there, go for it. Group shared memory is extremely fast. I believe it's up to 300 gigabytes a second. It's just mind-blowingly fast. You won't ever get close to those speeds with normal RAM memory. Third point, high arithmetic intensity. I'm going to go the other way now and say that you don't want to use memory because a GPU is just so damn fast at calculating things that often it's faster to actually just make the calculation than having to pull it from memory and then reading it back and transferring it and going through all the pipelines. And often it's faster to just calculate it. Fourthly, where what I was saying in the beginning of the CPU architecture, where you can have these massive pipelines of wide branches and if, else, if. You don't ever want to do that on your GPU. A GPU relies on having one simple set of do this, do this, do this, do this. And having a branch in that means that it has to do all that work, basically. It cannot take one path. In practice, it will take both paths and just discard the second result. You can do it for static data. Say like if my game-wide global variable is 1, then don't do this. You can do that. GPUs do optimize that away. But if you would have something like, if my particle is moving too fast, don't do these calculations. That's not an optimization at all. Don't use branches for that. And fifthly, there are too many optimizations here to put in a few slides. So really what you want to do is just understand the GPU architecture well. In my references, I will link to a couple of articles that will do a pretty good job at explaining it. If you know the GPU architecture and don't make any assumptions that you do on the CPU, you will be able to make more optimizations on yourself than you ever will from a few slides. All right, so finally, again, they did a pretty good job of making it straightforward, but there are some weird things. The buffer stride, so the amount of bytes in a buffer for each element, must be a multiple of 4. And that is really strict. If it's not a multiple of 4, nothing happens. That's documented. OK, thank you, Microsoft. But what they didn't document is that the structs in buffers, they have variables, so say the velocity of a particle. Those elements must have a stride of multiple of 4 as well. On NVIDIA cards, I should mention. This was a very weird bug and was hard to find out. What I was trying to do is use halves for my particles to save some memory. Halves are floating points of 2 bytes. And I had like 2 of them, so you ended up with 4 bytes. And why is it not working? I'm doing everything right. But it turns out that even the elements must be a multiple of 4. Thirdly, if you don't want your computer to crash, if you have a while loop with just a dynamic amount of iterations, terminate it in a timely manner or your program will crash, or in my case, my entire computer crashed. I had to pull the power plug cord out. Fun times. And fourthly, Unity, maybe they updated this actually, but at least in the first versions, they had this awesome error reporting where if you would do something wrong, you would get this error success. It wasn't actual success. Well, all right. And that's about it. So if you have any questions, you can contact me here or ask them right now. And if you do, I would like to ask you to go up to the microphone there, and so we can actually all hear you.
I've got a question about the shader code that you wrote. It looked like a typical HLSL type fragment and vertex shader. Is it possible to interface that with the Shader Lab surface shading model, like the lighting models that Unity comes with?
No.
Okay.
In a surface shader, they do their own vertex shader. And because you need to use the special vertex shader where you rely on the system variables and not on the mesh, I don't think there's a way to do that with a surface shader.
Is it possible to get the lights in the scene in a loop and just run through them and apply the color to them?
It is possible. I tried for TC particles and then failed miserably after a few hours. I was like, screw Unity. But yes, it's possible. I think Unity has some built-in shaders that do that, where you can see the raw code of how they do that in a vertex and fragment shader. So you might want to look into that and see how they interface there.
OK, thank you.
Hi. With the current state of support for GPU computation in Unity, do you think it's possible to have interparticle interactions and also collisions?
Yeah, it definitely is. For someone, this isn't public, but for someone privately, I did an N-body simulation, so where particles would attract each other. It's just a matter of figuring out how to program these kind of things, because you can imagine that it gets quadratically more complex. But there are a lot of good papers on that to reduce that complexity and to make those calculations fast. But it's definitely supported by Unity. Unity does everything that you would be able to do with DirectX 11 natively.
Thank you.
Right.
Hi. Do you think you'd be able to do something like image processing on a large image, maybe like contour mapping in parallel using these techniques?
Yeah, definitely. And that's actually the interesting thing of those thread groups. Because you could just make a two-dimensional thread group, you could easily launch one thread per pixel. And some of the benefits you gain from those compute shaders, like the group shared memory, and will actually really speed up some of the image calculations. I don't know for contour tracing if you will gain much out of it versus a normal image effect. But I do know that at least for like stuff like ambient occlusion, they have seen speedups of 20 times by using group shared memory for that. So yeah, it's definitely possible, and it's actually a really good use case.
Hi. Do you have to worry about lighting in Unity when you write out? Deferred lighting in Unity to write out to the right buffers?
To write out to compute buffers?
Well, you're writing out in your pixel shader to the screen buffer, I assume. But if you're using deferred lighting in Unity, do you have to worry about the other buffers that you might need to write out to?
Not really, I believe so. At least I know that TC Particles runs in dereferred using these same techniques. I think that since it's kind of done after the fact that the most stuff has drawn, here I can show in the CPU code, is being run in on-render object, which actually in the Unity pipeline gets called after most stuff has been rendered. So you will see that by that point, the scene with the dereferred lighting probably is already done. So you don't have to worry about interfering with that. All right, I think that's about it. Thank you very much for your time.